Hello, all. Welcome to the third part of the tutorials on Pytorch. In this part, now we shall be looking at the training procedure and then the evaluation procedure. So, now what do we mean by training? Now, we need to obtain the optimal values of the parameter. And how do we do it? Now, we perform the forward propagation, compute the loss, perform the backward propagation so that we obtain the gradients and then we update the weights. Okay, this is the standard procedure. Okay, now, and how will we be doing it on all the examples? No, we will be using a batch of the examples. So now let's just make a note of it. So now the first thing is how many times you want to iterate over the whole data, which is the epoch idea. Okay. Now for E in range number of epochs. Okay. Now I'm using Python like struct code here. And then so for so many epochs, you want to iterate over the data. Okay, and then we will be dividing it into batches. Okay, the whole data is divided into batches. Now, since the whole data is divided into batches, for each batch, I'll take it, perform the forward pass, perform the backward pass gradients, update the weights. And then for the second batch, for the next batch, I'll be going ahead with the updated weight. Okay, now then, let's say that there are batches. Okay, now my whole D which is there is my whole data which is there is having small batches. Okay, then for D in D, now here D is a list of all the batches. So one after the another. So it will be assigned. So now what is the first thing that I'll do? Now I have X for the given batch. Now this X which is there is features, and the Y which is there is the target. Now first we predict Y hat. Now how do we predict? Now it is we have declared a model. So we use model of X. Okay. Now you get the prediction and then you compute the loss. Okay. Now how do we compute the loss? Using Y comma Y hat, the actual and then the predicted value that will give us the loss. Okay. And then once we have the loss, then we use backward. Now we use backward to obtain the gradients. Okay. And then we update weights. Okay. Now, this you will repeat again. Now, for the second batch that you get, you will be working with the updated weights. Now, so on and so forth. Now, how many batches are there? Now, in one epoch, so many times you will be updating the weights. Okay. So, normally this is what is said to be iterations. Now, one iteration is one weight update. So, in one epoch, you can have multiple weight update depending on the batch. So, now to perform this, now there are certain things that you have to decide. Okay, now which what we call as the hyperparameters. Now, what are the hyperparameters that we want to decide? Now the hyperparameters. See, what do I mean by hyperparameters? Now these are not learned parameter. No, these are just you are considering them. It's a value. Okay. Now the first thing that we should consider, the first hyperparameter that we should consider is the learning rate or the step size. Okay. Now then you should decide on the batch size. Now we have to decide, and then how many epochs now we have to do. Now these are the choices that we have for the hyperparameter, the basic choices, and the basic architectural choices. Okay, the arc choices that we have number of hidden layers, and then number of nodes in each layer, number of nodes in each layer we have to decide, and then the activation function. These things needs to be decided in terms of the architecture. Now, since we have created the model, now we have made our choices. The number of hidden layers we have taken 2. So number of nodes in each of the hidden layer, we have taken 512, 512. Now, activation function, we have taken the ReLU activation. So these things we have decided while making the architecture. Now then the optimization choice, okay, then comes the choice of optimizers, the optimization choice. See, there are multiple now variations of the gradient descent. Okay. See, one problem that you can see with the gradient descent is now across all the epochs, for all the parameters, the learning rate actually will be the same. So now the question arises: is there a way in which we can dynamically obtain the value of the learning rate based on the previous gradients, okay, based on the previous directions and the steepness of those directions. So now can we actually obtain the gradients, the learning rate, okay. Now that give rises to the choice of what is known as different optimizers that we have. Couple of famous optimizers that we have is Adam. There is one more thing called as RMS prop and SGD, which is the vanilla one. Okay, so now we'll be shedding more light on this. So now in the theory sessions, okay, now we will be discussing this in detail in our sir will be discussing this in detail. Okay, so for now, let's just use Adam. Okay, because that is the one which is very nicely performing optimizer, and then we will see how does from SGD Adam actually developed. Okay, now these are the different choices that we will be having before going ahead with the thing. Now, couple of choices that we have already made is this. We have made the Adam choice. Now, the only choice that are left with are the hyperparameters. Now, in which I have to look at the learning rate, batch size, and then the epoch. Okay. So now let's do that. So now I just need to run all these ones and see whether change runtime T4 is there. Good. This is it would have disconnected because we haven't used it for some time. So I just need to rerun the things. So it is getting connected. These are the prerequisites code. I need the CUDA device, and then the network is needed. And then I have created the network. Okay. Now this is done, and then I have the data with me. Okay. So now here, and one important thing that we should remember is we have the data set. So now we haven't converted them into batches. Okay. Now this part is what is known as creating the data loader. Okay. Now whenever we have data loader, now that means that we have created them into small segments of batches. The data set which is there, that we have converted into loaders. Okay. No, so now let's do that. Train loader equals torch utils data loader. I will take the training data. Now batch size, now I'll just keep it as 128 and shuffle equals to true. Now what do you mean by this shuffle equals to true in the sense? See, for example, let's say that example 1 is in first batch, in the first epoch. Now second epoch, it may not be in the first batch. It will be shuffling. Okay, it might go to some other batch. Okay, that is what is known as the shuffling equals to true. So whenever we are dealing with the test loader, which is just the evaluation, you just evaluate it once. That is what is inference. There, we don't need the thing to be shuffled. Okay, I'm considering the batch size as 128. And please remember that the network that we have is independent of batch size. Okay, whether you have batch 32 or batch 64, the same network will work. Okay, now because batch is another dimension. So whenever you put all of them together, you have 128. Now you have 128, 128, 28. That will be the size of your data. Okay, now the network that we have is independent of batch size. Okay, so now we have all these things in hand. So now the next thing that we need to be doing is these hyperparameters. Now, what are the hyperparameters that we have? The learning rate. Okay, so the learning rate. Now, normally, now we have certain standard starting learning rates. Now, for a classification problem, we always take 1 e to the power of minus 4. Okay, for classification problems. Okay, so and then batch size we have already given it as 64, and then I'll take the epochs as 10. Okay, and then we have to next we have to decide on the loss function. Now, since we are dealing with a classification problem, the loss function that we shall be using is cross entropy. Okay, so how do you do it? Nn dot cross entropy. So and then please remember, for this cross entropy the input is logits. Now you to give the logits, it will internally convert it into softmax. You don't need to convert it into softmax and give it here. Okay, nn dot cross entropy, you just give it. Now then the optimizer is torch dot optim. Adam is the optimizer. Now for all the parameters, I'm using the same optimizer. Now that means that you can have multiple, for the same network, you can have multiple optimizers for different parameters. That is possible. Okay, theoretically it is possible. Okay, so and then you define the learning rate. Okay, so now we have everything now. So now we have to write the training loop. Okay. Now we will do it for one epoch, and then we'll have a for loop and then repeat it multiple times. Now def, I'll write the function train loop. Now what are the input for this? Now, the input is the data loader. That is the first one. And then you need the model. You need the loss function. We need the optimizer. Okay. Now these are the basic things that are needed. Okay. Now first, now we have to have some kind of a bookmark. Now, just to see how the loss value is changing. Okay. Now to do that, okay. Now we should know the total number of examples that are there in a given data loader, and then so that you can divide it and then come to know now what is the loss. Okay. Now for that I need the size. Now this will be, okay, this is the length of data loader dot data set. Okay. So now for batch x comma y in enumerate data loader. Now enumerate now will give you two outputs. Now one is the first, it will give you the index, and the second one will give you this x and y. Now this is your features. Now this is your target. Now this will give you the batch ID. Okay. Now you're iterating through your data. Now what is the first thing is your prediction. Now your prediction is model of x. Okay, this is your prediction. And what is the next step? Now you have to compute the loss. Now loss is loss function of y. Now this is the loss computation. Now then we have to look at the back propagation. Okay, so now while doing the back propagation, there is one thing that we should remember. Okay, now That is optimizer.zeroGrad. Now, what is this optimizer.zeroGrad? So now this particular thing, this particular method, what it will do is for all the parameters in that optimizer, now in our case, the whole model, okay, all the gradients of the models are reset. Okay. Now, why it is needed? Now, there is an issue of gradient accumulations. Now, gradients by default always adds up. Okay, to prevent double counting. Okay. Now, therefore, what do? We explicitly zero them after each iteration. Okay. Now, otherwise, what will happen if you do multiple iterations? No, it will by default adds up. Now, we don't want that to happen. Why? We are not doing any kind of gradient accumulation. Now, if you want to do some kind of gradient accumulation, now what do you mean by gradient accumulation? See, whenever you have a very huge model, sometimes we will run the model multiple times, accumulate the gradient, and then do back propagation. Okay. Now, for each update, we are doing the gradient back propagation. So the update. So we don't need to go ahead with gradient accumulation. Okay. Now that this is to zeroing out all the gradients. Okay. Now then loss dot backward. Now we'll create the what do you call? We'll obtain the gradients. Okay. And then optimizer dot step. Now it will perform the update. Now this is the gradient computation, and this is weight update. Okay. And then what do? We need some kind of a tracking, otherwise we don't know what is happening. Now, if the batch that we have is of some multiple of some 100, so just to keep track of the thing, now I get the loss. Okay. So loss item will go here, batch. Uh, so now current. Okay, I don't need the current value. I just need to see that what is the loss at that point. That is enough. Print the last thing. Okay, okay, let's compute this. Current is equal to batch into length of thing, and then you divide it. Okay, now that will just give you an indicator of how much you have obtained this. Okay, fine. Uh, okay, fine. Now this is the training loop. Now there is one thing that we always put here now, which is model dot train. Okay, so this why do we do this model dot train? Now, this is to set the model in the training mode. Okay. Now, whenever you have dropouts, those are regularizers, and then batch normalization. Whenever in the model you have these kinds of designs of dropout or batch normalization, at that time you will be needing to do this. Okay. But in this situation, we don't have dropouts or normalization, but it is just the best practice to put it. Okay. This is the training loop. Now then, how do you perform the evaluation? Test loop. Okay. Now even for the test loop, again, you want the model, loss function, and then the data loader. You don't need optimizer because anyhow you're not going ahead and updating any weights. Therefore, you don't need the optimizer. So number of batches and size you can obtain. And then, so we have to keep track of loss, and then how many values we are able to correctly predict. Okay. Now, what is the loss? and then how many examples in the whole data loader. This is the total size. How many of them I am able to predict properly. Now we just need to keep a track of it. This is when you have size, the overall examples, and then you have the correct number of totally correctly classified examples. Now you can easily find the accuracy. Okay, or okay, if you are dealing with any binary classification problem, then you can go ahead and find precision recall or F1 score that we have discussed earlier, and then you can obtain your ROC, AUZ, all those things, metrics that you can easily obtain. So we have dealt deep into those ideas in our earlier tutorials whenever we are dealing with the base classifier. Now, if you're not having a two-class classification problem, then how do you do it? Now you can consider one versus rest idea and then do it. Okay, so now let's proceed. Now, whenever we are evaluating, now we have to put the model in eval mode. Now, again, this is a best practice. Okay, so now, and then we put it in torch.nograd. Why? No, because I don't need any kind of gradient tracking. Now, why do I don't need any kind of gradient tracking? No, the sole reason is we are doing inference. Okay, the gradient tracking with respect to the computational graph is only needed now whenever you want to update your parameters. Now, in this case, you are not trying to update the parameters, so we don't need any kind of gradient tracking. Therefore, we put it torch.nograd. Okay, so now then inside this, for x and y in data loader, first you predict, okay, and then the total loss which is there, you go on adding. Okay, now loss dot item, that means that this loss which is there is computed on the device. Now please remember that. Okay, it is computed on the device. Now therefore now you have to put it as an item so that it converts into a Python thing. Okay, now then how many of them are correct? So now correct plus equals, that is correct is equal to correct plus. Now you take the prediction and then you take the argmax of it. Okay. Now your prediction, you have a batch. So this will be a vector of some 128 dimension. Your y is also a vector of 128 dimension. So this, whenever you take the argmax, now you get the labels, the predicted labels. Now that you are performing a relational comparison with the y. Now you have a vector of size 128, that is your prediction. You have a vector of size 128, that is your actual value. Now individually you obtain. So a relational operation will give true or false. Okay, and true is considered to be 1, and you convert it into float. Now whenever you convert it into float, what happens is true is becoming 1 and false is becoming 0. Now that means how many ones are there, how many examples that are predicted properly, and you take the sum, that is number of examples, dot item, just to convert it into a Python numbers. Okay, now this will be able to tell us how do you obtain the number of correct examples. And then finally, now once it is done, then you will compute the loss for a batch, and then you will just make a print. Okay, now average loss is now test loss. This, just make a print of this. Now this is the test loop. Okay, the training loop, now wherein which prediction, loss computation, optimizer dot zero grad, so that the accumulated gradients are reset, and then loss dot backward, so that we obtain the gradient computation, optimizer dot step, where which the weight update happens. Now here, prediction, loss computation, and bookmarking of the loss, so that we can understand how much overall loss is there, and comparing and obtaining how many in the given batch we are able to predict properly, and accumulating them and dividing by the total size so that I know the accuracy. Okay. Now this is the training loop and then the testing loop. Okay. So I have created the functions. Now the thing is, now I have to actually just run it. So now for E in range of epochs, now print, just print that f epoch e plus 1 of epochs. Okay, and then you have the train loop, in the train loop. Then you have the test for after each epoch I'm performing the test, and then I'll print training complete. Okay. Runtime error. Good. All tensors should be expected on the same device. Now, why is this error coming? Okay. Now, the reason is, model we have ported onto the device, but X which is there, we haven't ported onto the device. No, that was not done. So, we have to add X is equal to X dot to device, Y is equal to Y dot to device. If you don't have it, you will get this error. Okay. Now, as I keep on telling, all the model and everything should be on the same device. If you have everything on the GPU, have everything on the GPU. If everything is on CPU, have everything on CPU. Okay. Now, you cannot have in between like that. Now, you can see that epoch for every 100 thing. Now, you can see that the loss is decreasing. Now, the test accuracy after one epoch is 91.9. Okay. The accuracy should increase and the loss should decrease. Okay. Now, an MLP is able to solve the MNIST problem. See, now the loss is decreasing and the accuracy is increasing. Okay. See, sometimes there might be a very small fluctuations in terms of loss. So we don't need to worry about it. It happens. As you can see here, from 0.12 it is going to 0.16, but that's fine. It happens. Okay. Small fluctuations like this will happen. Okay. Now this is the first MLP that now we shall be running on the MNIST data. Okay. See, now we have significantly reduced. So the training is complete. So after 10 epoch, we have got 97.3 accuracy. Now that means that out of 100, out of 1000 examples, I have got 973 examples correctly classified. Okay. That's what it means. Okay. Now the training is done, and then the inference, we are doing it for each time. Okay. So now how do you save this model? Okay. The model, now what do you mean by a model? A model is nothing but bunch of weights. Now see, each of the updates, now what is happening? The parameters are getting modified. Now you have to save this parameter so that if you want to use it again on the same data, now you don't need to retrain it again. You can take the trained model and work it out. Okay. Now, how do we do it? Torch dot save. Okay. You can say that everything. You can save it like this. Model dot state dictionary. Now you are saving it as model dot pth. You can save it up like this. Okay. And then how do you load it? Now loading is again simple. You create the instance of the model, and then you have to use what is known as okay, this is how you save it. Okay. So now let me create a new model. Model 2 equals neural network dot to device. Okay. Now you create it, and then you load the model. Model 2 equals, so torch dot load from model dot pth. You just load it. Okay. So now what we can do, we can directly run the inference. Now test loop. What are the things that we need? We need the model. I'm sending the model to, and then the test loader, and then the the loss function. Okay. Is it in the same order? Oh, okay. The order is different. So this is model 2. I'll just run it. Oh, okay. This is the reason. Okay, got it. So I have saved it in a different format, because of which this is happening. Okay. So now you have saved it as saved dictionary. That is should not be the case. Most of the times we just save the model. Okay. Rerun it, saved the model, created this model.torch.load. Here we have to use weights only is equal to true. Okay. Oh, sorry. This weights only should be false. Sorry. Okay. Yeah. Weights only should be false, and then you run it. So you get this 97.3. Okay. This is how you save the model, and then you can reuse it. So you just need to create the instance of it and use it. So now that means now this gives us a straightforward idea that now this is what is known as the pre-trained models. Okay. Now whenever we hear these terms pre-trained models, now they release the weights, and then if you have the instance of the thing, you can just load the weights and then you can perform the inference like this. So you don't need to worry about the training. Okay. Now that is what we shall be looking at in the next thing. Now, wherein which we'll be considering the pre-trained weights of one of the very famous data sets known as ImageNet on all these huge models like VGG network, ResNet, and then we'll be reusing them. Okay. Now this is the overall idea. Okay. So you should have the data set, model, and then the training procedure that is there. Now perform the training, save the model, and then that save the model in the sense, save the weights of the model, which can be reused for inference like this. Okay. So with this, we conclude the idea of MLP. The next thing that we shall be taking in the next part of this Pytorch tutorial is we'll be looking into CNNs, convolutional neural network, for the same problem of image classification of MNIST. And then post that, we'll be considering some of the famous architectures like VGGNet, ResNet, and things, and then we'll work it out. We'll code them up. Okay, that comes in the next part of the tutorials. Hope you enjoyed this part of the tutorial. Now, welcome to the club. You have ran the neural network for the first time. Okay, now welcome to the club. Thank you all. Bye bye.